brought some rocks in, and I love that you guys have name tags. Raven brought some rocks in, and we were working on identifying some of them, so we can use yours as well.
Yeah, and all of them are identified except for one, unknown.
Good idea, but again, she won't let me break it, so it's a surface to look at. And I just wanted to make an introduction. Tracy, back in the corner there, is a student at University of Northern Colorado, and she's doing an internship with me. So she's just going to follow me around today and see what we do on field trips. So geology, well, does anybody know what geology is? I'm going to start just with, since it's a geology day, kind of.
Study rocks.
Study rocks, what else?
Landforms.
Landforms? Geo actually means earth, so geology is the study of the earth, so that can encompass a whole lot of stuff. But geologists like their rocks, so lots of rocks, lots of landforms, things like that. The Denver area is a spectacular place for geologists because we can see almost any type of the common rocks in the area. There's not a lot of vegetation, so because to me, it's like, oh, the plants are in the way of my rocks. So I like being out here without vegetation covering the rocks. But as you probably have learned in some of your classes, this is, particularly this part of Denver, is just a great place to be, and there's just so many things that you can do out here. Things to show people, which is why you're here. So what I thought I'd start out with was a little bit of how to describe rocks or how to identify rocks, because I think they didn't get a lot of that in there. Okay. So I have some rocks up here which you can come look at, and the rocks that are on the table are some of the rocks we're going to see today. But I want to give you just a quick overview of the 3 rock types and try to explain a little bit how to identify some of the more common ones of those. So let me just write some stuff down and then I'll talk about it all. I'm going to run it over. So this is just, because we could spend months talking about rocks, so I'm going to try to condense it all into about 10 minutes or 15 minutes. But you'll have, just so I can talk about a few other things before we go to Roxborough. But we'll point things out as we go along, and feel free to ask questions. So, and my handwriting stinks. So the first group are called EPS rocks. And those are the rocks that form from magma or molten rock. And there are many different types, but I just picked 2, probably the 2 most common, which are called basalt and granite. And thanks to Raven, we actually have an example of basalt here. This would be the type of rock you would find in Hawaii. Anytime there's a lava flow or a volcanic eruption, one of the rocks you're going to find is basalt. And it's my favorite type of rock, even though to most people it's black and nondescript. But this one also has some holes in it that form from gas coming out of the lava as it cooled. It kind of bubbles out. If you think of oatmeal, nobody makes oatmeal on the stove anymore, but if you've ever done that, or a stew or something, and you see the bubbles come up to the top and they pop, same thing happens in a basalt. So when you see a lot of these holes, that tells you that this rock had a lot of gas in it, and the bubbles popped as it was cool. Now, not a lot of basalt in this part of Denver. If you get closer to Golden, some of you may have seen the Table Mountains behind the Coors Brewery. That's that nice flat top mesa, mountain kind of thing. That's a lava flow, and that's going to be this kind of rock. And again, I know I'm going through this very, very quickly because I only have an hour. So if you have any questions, let me know. Because I'm throwing all sorts of rock stuff at you all at once, I know that. Okay. So a granite. There's granite out here. And so you'll be seeing a lot of a rock that looks like this, or looks like this, or looks like this. Actually, let me go grab my other one. Granite, very, very common, but it can look very, very different. But if you see a rock that's got a lot of pink stuff in it, and you can actually see individual crystals, that's probably a granite. And again, we've got extra pieces up here, and these two things, if you want to look at them a little more closely later. And when we walk around here, we can do a little more rock description. We'll actually go out and look and walk around and make a look at some of the rocks that they've brought in to line the trail with. Oh, thank you. Good idea.
Touch and lick and smell.
So, the thing with the igneous rocks is, even if you can't identify anything in here, when it comes around, you'll at least be able to see specks. So that tells you you have things in there. And the specks, especially in this one, the pieces are a little bit bigger, they're crystals. And that's one way we identify igneous rocks. Do they have crystals in them? So like I said, feel free to ask questions, because I know I'm going through this way, and you're probably going, what is she talking about?
So what's the composition of the one in your left hand, the black crystal?
The black is...
versus the lighter color?
Okay. Geologists really identify rocks based on the minerals in them. So the black mineral is a mica. And some of you are probably familiar with mica. That's the stuff that you can peel off. It's really shiny. You can scratch it with your fingernail. So that's a mineral. And there's lots of mica in this area. And we've actually passed around some of Reagan's rocks because she brought some with a lot of mica in it. And that's this silvery stuff. It's really shiny stuff.
So is that also granite?
That little piece is a type of granite, yes. And what we also have in the granite is quartz. Quartz is a very common mineral. It can be white. In that granite, it's actually kind of a clear color. So sometimes quartz in rocks, because it's clear, will look gray because there's a dark mineral behind it. But you can also find quartz looking like this. You can find quartz looking like this if it's very weathered. You can find quartz looking like this. Okay. So I'll pass this on. This is a nice sample of a big piece of quartz. The other thing we have in granite, yeah, I was looking, there was one that has some really nice feldspar crystal in it.
They're round.
The granite, that's just what I was going to talk about next.
Yeah.
Oh, good question. So I'll take this up. But if you look at some of it's a mineral called feldspar. I should write these up, shouldn't I? Let me put the mineral names in a different color. Not in white. Feldspars as a group are the most common minerals. So most of the rock, they make up about 50% of the rocks on the Earth's surface. So most rocks you pick up are going to have probably at least one feldspar in them. That's what gives the quartz its pink color. There's a type of feldspar that's pink. If you look at that other granite that's coming around, the feldspar can be really annoying because it also can be white. So sometimes you get the pink feldspar, that's quartz. Yep. Quartz can look like anything it wants to practically. Quartz can be white, it can be pink, it can be green, it can be yellow, it can be purple, it can be black, it can be orange. Quartz very commonly will be clear or white in a rock. But yeah, any color it wants to be. So the pink feldspar, or the pink feldspar is very, very common in rocks, in granites, but it doesn't always have to be. Again, in here the feldspar is white, which makes it sometimes a little tricky to distinguish from the quartz. One of Raven's samples, which I want to point out because it's got very lovely feldspar crystals. And when we take a break right before we go to rocks where I can point them out, this actually granite sample had really nice feldspar crystals in it. The nice pink, and you can see they're really nicely shaded, which gets geologists excited. I picked this up and I'm like, those feldspars. So just if you want to see what a pink feldspar looks like when it's really, really nice, there's one right in one of Raven's talks. So those are just two of the many EPS rocks, but these are the ones that you're probably most commonly going to run into in the Denver area. So on that little bit of information, any questions? Probably not, but again, as we go around, we'll point out, because I came out and previewed the hike last weekend, and there are a lot of very nice rocks that they've used around here to line the trails with. So we'll do some rock identification after lunch as we walk around this area. But the second type of rocks are called sedimentary. And these are rocks that are made up of broken down pieces of rocks and minerals. If you think of the way we make cement, humans take pieces of rocks and put them in some kind of goop that glues them all together. That's what a sedimentary rock is. It's pieces of other rocks that have been broken down, maybe rocks, minerals, fossils that have been glued together. So sedimentary rocks are made from other rocks. And conglomerate, an example of that would be cement. Because we name sedimentary rocks based on their particle size. So conglomerate would be an example of, or cement would be an example, sorry, of conglomerate, a rock with kind of big pieces that have been glued together. Another type that most of you may have seen is called sandstone. So sandstone is made up of sand-sized material. You think of like a sandpaper. And I have lots of sandstone here. And you'll notice as we pass this around, it feels grittier, kind of sandy. And we have different colors of sandstone depending on how much iron was in the rock when it formed. So when you see this red color, like in the red rocks, those rocks had a lot of iron in them. And the iron was oxidized when the rock was forming. So the rocks rusted. So this rock has rusted. This is a sandstone, had a lot of iron in it, so it's rusted. This is a sandstone that obviously hasn't rusted. And the reason I brought these two is when we go to Roxborough, we're going to look at the hogbacks. And the hogbacks in this area are made of different types of sandstones.
Why do they name hogbacks? Why the hog?
Somebody thought they looked like a hog.
Okay.
The back of a hog, kind of like the razorback. Yep. So you'll hear me talk about the fountain formation, and the fountain formation is going to look a little bit like this. It's a reddish sandstone with some pieces in it. The lions, it's going to look, and the Dakota are going to be sandstones that look more like this lighter colored sandstone.
And what causes the iron to be oxidized versus not oxidized?
If it forms, if there's a lot of oxygen in the environment when the rock is forming, it would look like this.
Okay.
So it tells us, this is useful because the color of the sandstone tells us a lot about the oxygen in the environment when the rock is forming. Because if you think about what a geologist is, a geologist is basically a detective. But instead of going, let's be icky for a minute, like a CSI to a murder that happened maybe a couple days ago, we're looking at rocks that formed millions of years ago. So our rocks are the history book of the planet. And the nice thing about sedimentary rocks, because of the way they form, give us a lot of information about what the environment was like. Was it wet? Was it dry? Was it hot? Was it cold? Was there a lot of oxygen? Was there not a lot of oxygen? So for a geologist, our crime scene, I guess, is the planet, and our evidence comes from the rocks. So we spend a lot of time trying to figure out what the rocks are telling us. Yes?
I'm curious about, that piece of sandstone was formed later than the grains that make it up.
Yes, yes.
So is the oxygen from when the sandstone was created or when the prior rock was?
Good question. Well, something I kind of skipped over, but what he pointed out, the sand grains in the sandstone have come from another rock. So the sand grains are older than the rock. And then they got broken down, maybe put in a river, carried somewhere, dumped, and then turned into the sedimentary rock that we see. So the red color comes from when the sandstone was actually forming. So it's that deposition. What was it like when those sand grains were deposited somewhere and that was turned into a rock? Now there are a couple other types of sedimentary rocks that I didn't put up here, but I should put up the limestone, I guess. Because we also have sedimentary rocks that can form from water. You get a lot of material that sits in water. It can fall out, precipitate out, fall to the bottom of a river, lake, ocean, and kind of that goopy stuff at the bottom of the lake or the ocean. That can get squished and turned into a rock. So we also have sedimentary rocks that aren't made up of pieces of other things. And the limestone is a good example of that, which I was telling them I'm feeling kind of stupid today because I had a second box of rocks that I totally forgot until I got here. But hopefully we'll steal limestone somewhere along the trail today. Limestones are kind of easy to identify though because they contain a lot of calcium carbonate. Sorry, I'm throwing way too many terms, aren't I?
No.
But the fun thing about calcium carbonate, anything that has this CO3 in it will react with acid, a weak acid. So it's kind of fun to show kids. Geologists always have a little bottle of acid with them because there's a lot of this calcium carbonate in the environment. But you drop some acid on it and it will bubble. And so that's one way we know if it has calcium carbonate in it.
Is there any way you can tell just by looking?
Not really. Because what can happen, what we get a lot, not only does it form rocks, but it can come in late in cracks and fill in cracks, and it can also form coatings on rocks, and it can look a lot like quartz. So a real easy way is just to dump some acid on it. And if it bubbles, you know you've got calcite. Plus, it's just kind of fun. You can do the same thing with Tums. If you go home, and I should have brought it actually, you take some Tums, drop some vinegar on it, it'll bubble for the same reason, because Tums are calcium carbonate. Ooh, I'm going to sneak in some really quick chemistry on you. Do you know why Tums is called an antacid? Because it reacts with the acid in your stomach. So the same reaction we can do with calcite outside is why we use Tums. And it reacts with the calcium carbonate and releases CO2. That's what the bubbles are. And this is always fun for kids, so that's why I'm going to be a little improper. But a lot of people, when they take Tums, they notice they get gassy. And that's because the CO2 is being given off. And that's why you burp when you take Tums. So, of course, that's fabulous with little kids. Because they're burping. The other thing about limestone can be tricky because it can be inorganic, like it just precipitates out of the water, or it can be organic. So a lot of times when you find a rock full of fossils, that's limestone as well. We call it fossiliferous limestone, to give you a big fancy word. It's just fun to say. That just means a rock with fossils in it. So the fossiliferous limestone, so our third type of sedimentary rocks that we have, would be those sedimentary rocks that come from some kind of organic material. So a rock. So we really have three types of sedimentary rocks. But the one that you're going to see, that you'll see most in the Denver area, is this first group that's made from the pieces of other rocks. Because we have a lot of sandstone in this area. Yes?
What about shale?
Oh, thank you. Shale. No, that's good. Like I said, I'm trying to throw this all in so I'm going to forget stuff. Shale is also like conglomerate and sandstone. It's made from the pieces of other rocks. And with shale, the pieces are very, very fine grained. So shale is made from mud-sized material. And if you've not been to Dinosaur Ridge, I would suggest you go. I know, Amber. So, but one of the things you can see, especially when you get on the kind of the Morrison side, is they have the Morrison Formation there, which has sandstone and shale. And if you walk along the pathway or along the road, you can see where the shale is washed out and turned into mud. And if that gets buried, that's going to turn right back into a shale. So shale comes from mud-sized material. Sandstone comes from sand-sized material. So I only have one piece of shale, but I'll pass it out. So shale generally doesn't last in the environment very long because it breaks down very, very quickly. And we'll see an example of it when we go to Roxborough, because a lot of the valleys that we see in this area are underlain by shale. Because those rocks have been broken down and eroded away, and so it forms a valley. And one of the things we'll look at with Roxborough is how the types of rocks that we see out on the landscape actually form the landscape. You know, which ones form hills, which ones form cliffs, which ones are going to erode away and give us valleys.
You're going to talk about that on the trail?
Yeah.
Okay.
Excuse me, I have a cold, so. But shale is a very good valley former. It doesn't hang around very long, it erodes very easily. So often if you see a valley, especially in this area, it's going to be underlain by shale. So I'm going to pass, like I said, I only have one, but I'll pass that around. And you don't see the number on here. We don't talk about where I borrowed it. Okay. So the last type is metamorphic rocks. And metamorphic rocks form from other rocks. Just like the sedimentary rocks do, but with metamorphic rocks, the rocks have been subjected to heat and pressure. So they form from taking other rocks and heating them up or squishing them, putting pressure on.
Is that where the diamond would come into that classification?
Yes.
Okay.
Excuse me. Diamonds form very deep, which is why they're not very common at the surface, because they'll form around 40, 50 kilometers deep. And it's very hard to get things up from that deep, but specifically just a diamond, which is why we don't find so many of them. Because they might be brought up with rocks, but they might be buried. So I'm going to start with slate. When we talk about metamorphic rocks, we can go from those that have been barely metamorphosed or barely changed from their original rock to those that have been really, really changed. And slate has not been changed very much. Slate comes from shale. So that mud, the rock that comes from mud, if we subject it to a little bit of heat or a little bit of pressure, it's going to turn into a slate. And slate and shale can look a lot alike. But one thing we can tell, shale's a little harder. Slate's a little harder. I can scratch this a little bit with my thumbnail, but I'm just leaving lines on it because shale, I could actually dig out a groove. The other thing, and this is called the tink, T-I-N-K test. If you hit shale together, it kind of makes that tink sound. This is one way. Whoops, I'm sorry. I'm leaving slate all over your floor.
That's okay.
One way, kind of, we first learn when we're first trying to tell shale and slate apart is it tinks. Slate will tink. So, again, I'm going to use Dinosaur Ridge again because there's lots of good examples of this stuff. There's a very nice, sorry, I'm switching rocks, shale that you can see at Dinosaur Ridge the way it breaks, it kind of breaks in nice square patterns, and that's why we use shale and slate for flagstone, for building stone, for stepping stone, because it breaks very nicely. Actually, out here in this courtyard, you can see that some places sandstone will also make very nice flagstone. Sorry, I'm skipping, I'm crossing genres a bit. So slate, this is metamorphic shale. So mud type of rock that's been subjected to some heat and some pressure. And it's made it a little bit of a harder rock. It's changed it a little bit. And metamorphic comes from, metamorphosis. And one thing you can do with kids, they're used to thinking about metamorphosis because of caterpillars and butterflies. So it's that same idea that you're changing something. Your schist went around already, right? I didn't bring a schist, but there's a little tiny piece that Raven has. So this is a metamorphic rock. It has a lot of mica in it. This one, this is a
So that
nice.
is schist.
That's a schist, yeah.
Anything else to say about it, or that's
It's been subjected to more heat and pressure than the slate.
it? Okay.
And the clay mineral, if you take mud and heat them a little bit, they'll change to clay. If you heat it and put it under pressure some more, it will change to micas. So the schist has been exposed to some more heat and pressure than the slate was. And now we're going to go to a rock that's been exposed to a lot of heat and pressure. This is called a gneiss. So that's the top one here. Gneisses, you can tell because they're going to be layered. So you can look at this one here. It's got black and white layers. And gneisses in composition are very similar to granite. So you're going to see some of the same minerals you see in granite, particularly mica and quartz. So when a gneiss is layered, it's either going to be black and white or pink and white. And it's layered. And this one also has lots of micas, because the micas get larger as the rock is subjected to more heat and pressure.
So does that mean that at one time, at least some of that was granite?
This could have been granite, yes.
So whereas the granite is more speckledy, the gneiss is more layered.
It's layered, yep. Layering is, gneisses by definition are layered. Sometimes they're really wavy if the rock's been exposed to a lot of pressure. And if you've ever been to Estes Park or Rocky Mountain National Park and seen the wavy rocks, that's what you're looking at. Because those rocks used to be buried to depths of about 30, 40 kilometers, and so lots of pressure, and the rocks just got squished. So this is a gneiss. I threw marble in just because we're not going to see it a lot in this area. But most people have seen or heard or maybe even have marble in their house. Marble comes from the metamorphism of limestone. And so marble also contains calcium carbonate.
That's okay.
And will react with acid, which is why if you have marble countertops in your kitchen, or maybe your mom had marble countertops, they tell you not to scratch them. Because there's a coating on there to keep it from reacting with acid. Because you don't want your real expensive marble countertop to break down. And think about all the acids we use in the kitchen. Coffee, tomato, soda, lemon juice, orange juice. All of that will react with calcium carbonate or react with calcite in the marble and break your marble countertop down. So I know this was just a really quick overview of rocks, and we'll go over different rock types again and talk about more as we go through the day. But if you have any other questions about rocks that you can think of right now, let me know. Or we'll also take some time if you want to look at the rocks again, kind of at the end as we're getting ready to go to rocks. Where we can do that.
Do you think we'll see a gneiss and schist in close proximity?
Not in place, but I think somewhere around, there are some big pieces. We're going to go to Waterton Canyon parking lot just to look at the big pieces that were brought in. They're not in place, but at least it gives you a chance to see some different varieties of rocks. This area some of you may or may not know, this was a gravel pit. A lot of this area was a gravel pit. We're on a floodplain, and so what we're going to see are a lot of sand and granite material that resulted from the weathering of rocks in this area. And at the surface, at least, there's not a lot of schist and gneiss. If we went way, way down, a couple thousand feet, we could find some schist and gneiss. But as we go out, and I'll point things in the hillsides, we're almost, sorry, I look at the hills. If you look at the hills, the kind of the hills in the background on the skyline, those would be granite and gneiss, because those are rocks that are about 1 billion years old. And they were exposed because rocks are generally laid down like this, one on top of each other. So the only reason we get such a good view of all the rocks that we could see around here is because as the Rockies formed, this whole area was uplifted. And so not only can we see, maybe I'll do it this way, not only can we see the rocks that were on top, but because this whole area was uplifted, we can see the rocks that are if we were to go out in the Denver Basin, it would be under 8,000 or 10,000 feet of sediment. And again, I'm sorry, I'm going to keep using Dinosaur Ridge as an example because it's such a good example. I mean, it's a world famous place. Because that area was nicely exposed when that road was put through, and so you can really see the younger rocks on like the C470 side, the older rocks on the Red Rock side. So if you haven't been there, go, because you can just see a lot of geology writing in one place. Yes?
You mentioned the gneiss in Rocky Mountain National Park. It was 30 to 40 meters deeper.
Kilometers.
Yeah, I'm sorry.
That's okay.
Yeah, kilometers. So that many miles.
Well, how did it come to the surface?
Yeah, was it that deep and came up, or did it go up real high and then was eroded down?
Both. I mean, see, I like his answer, but let me expand on it. So, one of the reasons we're lucky here is because of the uplift of the Rockies. That's brought a whole lot of stuff up to the surface so that we can see it. So, the things in Rocky Mountain National Park, you know, it's a little bit further west from us, so more up in the actual mountains. And all the things that were way down here would have been brought up, then uplifted into mountains and tilted, and then eroded. So all of that was going on. In fact, the reason that the same rocks that we can see in the hills out here are under 8,000 to 10,000 feet as we get closer to Denver is as the Rockies were being uplifted, they were being eroded. Now that all those rocks have been exposed to the elements, they're going to break down. The faster the rocks are uplifted, the faster they erode. So we had all this material just coming off of the Rockies, and it all got deposited in the Denver area.
Was most of the erosion due to glaciation?
Wind, rain, sun. Just think about if you get a scratch in your car or leaving a hammer or something out overnight, what happens to it? It starts to break down. That's what rust is. It's just exposed to the elements. Now, your hammer is going to rust in a day. The mountains and all the rocks around here took thousands, tens of thousands to millions of years to erode. So the minute rocks are exposed at the surface, they're going to start breaking down and wearing away just because of the wind and the rain and the sun and the snow and all of that. Does that make sense? So, like I said, a great place to study those. The Rockies did a lot of our work for us by bringing all this stuff up to the surface that we look at.
At this low elevation, is there much evidence of glaciation?
Not here, no. If you get a little bit up in the Rockies, a little further, you can see evidence of glaciers. And generally what geologists look for is, well, you've seen a sandstone. Glaciers carry a lot of debris because they erode it as the ice is moving. But you can think of the bottom of a glacier as being like sandpaper. And it might have different size grit on the bottom. So as the ice moves over rocks, it will scratch them. And if the sand or the grit on the bottom is very, very fine, it will polish the rocks. So we look for that kind of evidence. But you have to go a little higher up towards the Rockies to see that. But you can, once you get up in the actual real foothills to the Rockies, you can start picking up evidence of glaciation.
So we won't see any moraines or cirques or...
I'm trying to think, we might be able to see a cirque. Poke me when we get to Roxborough, we might be up high enough that we can see the Rockies. But sometimes if the sun hits it right, whenever you just see something that looks like a bowl carved in the Rockies, that's a cirque. So just anything that you see that looks like this. You can see them from 25, you can see them from around here.
There's that one.
Mount Evans, yep.
You can see from Chicago Lakes.
And if you ski, any of the ski areas, if you ski in anything that's called a bowl, that's a cirque. And for those of you that aren't familiar with that word, it's French. So a cirque is just a bowl. What happens is when glaciers form in mountains, they erode the rock. So the ice is starting to form, it's going to dig down, it's going to dig out this way, and it's going to dig out behind it. And that's what a cirque is. That's where a glacier started to form. And as it was getting larger and larger and larger, it was eroding the rock away around it. So it forms this bowl or this half circle kind of shape. So whenever we see one, that we know that's where a glacier formed, or at least a big pile of ice formed.
Do we have any true glaciers left in Colorado?
There is an argument, the Rockies notwithstanding. There are people that go back and forth that say St. Mary's Glacier is still a glacier. So there's a lot of discussion.
It disappears some years.
Yes, it does. As all glaciers. So. Yeah, so there's still some discussion about, whether that still is a glacier, because it takes at least a season for ice to form. And so it really depends how you form a glacier, how you define a glacier. And so different glaciologists will argue about the definition of a glacier. But essentially it's a big pile of ice that can move. It's kind of the simple explanation for glaciers. So that's why I said there's a lot of back and forth as to whether St. Mary's is still a glacier, and some people are making that point, well, it went away. So, but if it comes back and it has a couple of years and then it has the ability to flow, then technically it can be a glacier. Anything else? I know I've thrown a whole bunch of stuff at you.
We still have 10 minutes.
Okay. So I just wanted, before we get out and go to Roxborough, just wanted to point out a little bit about this area. This is actually a really cool area. We're in the lower foothills of the Front Range, right about 5,400 feet here. And have they heard about Chatfield, why it's important, confluence of rivers, all of that? Okay. So this is kind of a really cool area ecologically too, just because we're at the confluence of, I always forget it, Plum Creek, and the South Platte River. So that gives us a modern floodplain. But we're also in a place where grasslands are meeting foothills. So this is a really interesting place, obviously, to do a whole lot of science. So we'll look at some of those features today too, just what we're getting, because there's a creek, a river, mountains, grasslands all coming together. Some of the things, you're a little bit familiar with the fact that Chatfield's a reservoir, which also means there's been some human disturbance of the area, the dam, and all the effects that can have on the environment. We also have, I think it's awesome, they have a lot of beaver dams in this area. We're going to see one today. The two ponds that are out here that we're going to look at are gravel pits, so they used to do a lot of gravel mining here. One of the things you get in floodplains, actually this is perfect, are whenever you see rounded rocks like this, that means there's big water. They've been acted upon by water. And being at where a river and a creek come together, you get a lot of material being brought in that's about this size. And so humans mine it for gravel. So gravel is more of a size, not a composition. So depending where you are, depending what the rocks are in the area, it's going to color the type of rocks you see in the gravel. But this whole area was mined for gravel. I'm trying to think if I'm missing anything else about sand and gravel. Well, I'll think of some more probably as we walk around and talk. Oh, man, you forgot to tell me about this. Sorry, they asked me to do something that I did on the fly last year. Talking about how this area formed. And I talked about it a little bit. Just with the fact that we had rocks that were deposited and then uplifted during the Rockies. And turns out there have actually been 3 mountain ranges in this area. So the current Rockies are the younger ones. And we can see evidence from that. One of the hogbacks that we're going to see, let me make myself some room. To Roxborough, as you can see 3 of the hogbacks very nicely. And the rocks, geologists call rocks units formations. If you have a nice thick rock unit that has very similar characteristics, we'll call it a formation. So we're actually going to see hogbacks formed by the Fountain Formation, the Lions Formation, and the Dakota Formation. And the Fountain Formation formed from debris from the earliest mountain range in this area. If you've read anything about the geology of the area, you might have seen the term ancestral Rockies, but we're not really using that anymore because the mountains are kind of formed differently. So it doesn't really matter, but I'm not really going to say the ancestral Rockies. I'm going to say early mountain range just for that reason. But just like we have all the sediment now in the Denver Basin from the current Rockies, about 300, 400 some million years ago, there was an earlier mountain range here, and there was material coming off. And that material, that debris, was compressed and buried and formed what's called the Fountain Formation. And so we're going to see, one of the hogbacks we're going to look at from Roxborough is of the Fountain Formation. And the Fountain Formation is the rocks of red rocks. So when you go to Red Rocks and you see the rocks, when you go to Garden of the Gods and you see the rocks, that is the Fountain Formation, and it's a type of sandstone, and it's a red sandstone. And the Fountain Formation is about 360 million years old.
You said the number again?
360-ish. This is under discussion too. Whether it's about 360 million or about 380 million. So the Fountain Formation is the remnants of the first mountain range that was in this area. And then we'll see the Lions, which is a middle age, and then we'll see the Dakota. Man, I am giving you guys plugs today, aren't I? Which is 100 million years. And the Dakota is where the famous dinosaur footprints are. But these are all rocks that are resistant enough that when this area was uplifted by the formation of our current Rockies, which started about 70 million years ago, they were all resistant enough, and the rocks eroded out between them, but they're left standing as the hogbacks. So we're going to see, we won't actually get over to Carpenter Peak to touch the fountain, but we'll see it. And then again, we'll look at the Lions, and we'll be walking. Actually, we might be able to touch the Lions if there probably won't be the snow and ice this year that we had
Hopefully
last
not.
year. and the Dakota. And why was this area uplifted? So, I had mentioned before, let me do it this way, that our rocks tend to be deposited flat-lying. There's some, oops,
That's an earthquake.
that was an earthquake, thank you.
Continental drift.
That's the clay's too cold. But yes, I wanted to talk about plate tectonics, because I've been talking about things being brought up to the surface, and it's really tectonic movement that does that. So basically what we have here is we had all these very nice flat-lying rocks minding their own business, and then the rocks were disturbed. And so we have things that look like this. And then they were uplifted and the area was tilted, which is why we see the hogbacks the way we do. So this would have been better if I could have found the red clay. But this is kind of sort of what essentially what went on here. So we had layered rocks, the whole area gets uplifted, brought up to the surface as the rocks start to form, or the mountains start to form. And then we're here right on the edge of it, so all the rocks got tilted as well as being uplifted, which is why we can see so many of them. And what happens, and I'm going to have to cheat, is as these rocks get uplifted, the weaker rocks get eroded and go away. So then we have kind of the older rocks, we're missing the middle rocks, and then we have the younger rocks. So rocks that are more resistant will stay around, whereas things like shale will get weathered out and eroded away and carried away by rivers. So that was the 1-minute summary of the last 1 billion years of this area. But did that kind of make some sense? Just to try to set the stage for what we're going to see today. And this will make more sense when you actually get out and see stuff. It's hard to just, well, I have no idea what you're talking about and I can't see anything. So when we get out and look at it, hopefully this will make some more sense. So did I cover all of that? I did.
Nice.
When they said, we want you to cover all this and we want you to do it in an hour, it's like. And then the rest of the things in that handout were things I thought we would cover during the hike, or things that I wanted to try to remember to tell you during the hike. And again, you can always ask questions, because we're going to go look at a whole bunch of other stuff as we go out and around. And I have one more thing, just because I keep talking about rock deformation, and it's hard for people to think, well, solid rock, how can that be? So, silly putty, geologists also like silly putty. So, most of you probably played with silly putty. So, if you think of silly putty, we're used to thinking of rocks as being really solid. And so, if we go out and hit on rocks with a hammer, what are they going to do? Break. But, if you take the rocks and subject them to heat and pressure, and deform them slowly, what are they going to do? So this is how we get rocks uplifted. This is how we can get really wavy rocks, because if they are acting more like a plastic, or they're subjected to very slow deformation, then they won't break. All right. So, any questions before we go look at rocks, bro? We're all just kind of stunned.